am in data processing and data engineering teams at MIQ. I have been here for around 7 years, and before MIQ, I have been with Samsung and Vizuri. And the last 7 years here have been about building and managing different data management microservices, big data platforms for MIQ. So yeah, that's about me. And today I have with me my colleague Rati Ranjan, who has been the man behind actually implementing this solution. So I'll let him quickly introduce himself too.
Yeah. Hello, good people. I'm Rati. I am senior software engineer at MIQ. I have an experience of close to 4 years spanning across front end, back end, and data engineering alike. Pretty excited to be here. Over to you, Rohan.
Thanks, Rati. So moving on, here's the agenda for today. I'll just pause for like 10-15 seconds so that like you can go over the agenda items. Cool. So moving on. So who are we? Talking about MIQ, MIQ is a leading programmatic partner for marketers and agencies in the AdTech world. And AIQ is the main MIQ technology set which provides modular API-based capabilities to enable teams and individuals to rapidly build data solutions on top of them. So just to introduce a bit more, there are three major groups of capabilities that we have: Connect, Discover, and Action. So on the Connect side, if you see, it is a set of capabilities for onboarding datasets from a wide variety of sources, efficient storage of data as well as metadata, and also concerns with cataloging and governance of data. Discover is analytics at scale and refers to the set of big data technologies in the hands of our analysts, data scientists, data engineers to derive insights and trends from the dataset. And Action, finally, once we have the outputs received from the last phases, it can be used, the outputs can be used programmatically to affect our campaign strategies. And also the key insights generated can be used manually by the executives to devise their business strategies. So that's about MIQ. Moving to the next slide. So if you see in the right pane, you will see a polling section in the right pane. There you can go and choose the option. I'll read the poll question for you. So the question is, on average, what is the number of advertisements that a person is exposed to per day? And the options are 100, 500, 1,000, 5,000, and 10,000. We already see some questions, some answers coming in. Yep, pretty well distributed. Go on, folks. Few more answers. Okay. 500 is what looks like majority's choice. So yeah, so the correct answer, and folks, let me know if you're able to see, see the polling results. Yep. So the correct answer is, I do see few more changes in the votes or a few more votes coming in. So yeah, go ahead. Okay. So the correct answer is somewhere between 5,000 to 10,000 impressions or ads one person sees. So it might be surprising, but this is the average number of ads that we see as on average. And these ads we might encounter while by the means of billboards, commuting to work, ads on mobile devices, TVs, websites, etc. And 5,000 per person, multiply that with what? Around a billion devices, billion people and devices there. So you have 5,000 billion ads in a day. So you got a glimpse of the scale at which this ad tech data is operating and touching our lives daily. So today we are going to talk about a reporting solution that's operating on a subset of this huge data set that we are talking about. So to give you a better understanding of the problem statement, here is a very simplistic view of the use case we are talking about. So on the left side, if you see, there is a campaign management interface on which our traders and analysts and account managers manage settings for their campaigns they are running. And they do configurations like budgets for campaign, audience segments. They also do some programmatic deployments there, like programmable bidders, decision trees, etc. And these campaign metadata and configuration parameter needs to be joined with the near real-time log level data that we are receiving. So once these campaigns are running, we get like log level data like impressions, clicks, conversions, etc. These need to be joined with the like other metadata information that is coming from there. And on the second side, on the right side, if you see, there is a reporting application which is in hands of our clients, advertisers, agencies, as well as our internal users, which is like a self-serve reporting platform to analyze their campaign performance, their return on advertising spend, incrementality, all by themselves. So as you see, we have this ecosystem, but in between, the reporting application is querying the database, the transactional OLTP database directly, and that's the issue that we started facing. We started facing the typical OLTP reporting related issues. To give you few numbers, and this is the main part. The blue box that you see here is the like important part where which will be concentrating on in the next few slides. So to give you some insights about the numbers, so the kind of data we already talked about, and the numbers we had were like 10 plus databases, 650 plus tables, a billion plus records in a few of our most relevant tables that are needed, that were of our concern and for reporting purposes, and an influx of around 7 plus million new records daily. Uh, and because of the scale, we were facing into typical OLTP issues related to performance, like slowness of the database for heavy joins because the number of tables, as you see, scalability because we were limited by the number of campaigns which users could select for reporting purposes. And since it was a self-serve solution in hands of our clients and advertisers, the number of campaigns which a big advertiser or agency can have can be very, very huge. And we wanted to serve those use cases seamlessly without getting bottlenecked by the existing solution. So yeah, so before we, I think, go into the solution part, one more highlight was we did not directly jump into completely revamping the solution. We did try some short-term and like tactical patches, if that helps us, like scaling our MySQL nodes, scaling the concurrency there, increasing the parallelism in query, data partitioning, all of that. But even after applying these patches, only incremental improvements is what we observed, and we did not see any significant improvements. And that's when we decided to completely revamp the solution and take a fresh approach while maintaining business continuity, because it was a production important application for us in hands of our clients. We wanted to maintain that business continuity and do a graceful migration here. So uh, so on the requirements part, so when you revamp the system, you have your wish list of items that you'd want from the new system, and here was our wish list. So we wanted a system which has high throughput real-time processing capabilities for our events, efficient data storage layer which is suitable for our reporting purposes, and an efficient query engine for the dashboard which can serve within the defined SLA. And to understand it from the user's perspective, uh, or product manager's perspective, on the change propagation, any change that the trader or analyst does in the campaign settings should reflect in the reporting data with a lag of not more than 15 minutes. So any change that you do on the campaign management, I think, application that you see on the left side, that change data should reflect into the reporting system within 15 minutes. And on the reporting side, for a better user experience, when you are loading different dashboards, the worst case SLA for loading any kind of complex dashboard or anything like that should be not more than 8 seconds to give you a better UX user experience. And on the future scale projections that we had from our product team, for next 1 or 2 years, it was around like 2 times increase in the data volume in terms of increase in the number of campaigns, data for each campaign and all, and 4x increase in the number of concurrent users. So cool. So with all of these wish lists and requirements in mind, we went ahead to like have some tech design considerations and tech choices that we wanted to have. So on the change propagation side, we needed a real-time change data capture system for change propagation, and that choice of technology was around AWS DMS, which helped us do the CDC, and Kinesis to serve as a middle layer for from where the processing engine can consume the data. On the real-time processing bit, because we needed to join a lot of the real-time stream joins that we do and denormalize the data in real time, uh, we needed a system which can process millions of events per batch. And for that, we went ahead with Spark streaming, always running Scala app on Databricks, and it was able to serve us for that. And next, we needed a query engine, which is high throughput, high concurrency query engine, which can serve the dashboard queries, which use datasets complex joins within 8-second SLA. And for that, we went twofolds. Like one was efficient storage in form of Delta, and then we went ahead with the SQL Analytics query engine, serverless SQL query engine. And we needed the system which we could be confident of the future scaling needs of the next 2 to 5 years, and all these choices we have taken here can be horizontally scaled. So with all these like choices and everything, the new system looks something like this. Remember the blue box or black box, whatever you call that. uh, that that box is replaced with the bottom set of technology that you see here, and that's how the new system looks like. So you have previously there was only this MySQL database. Now you have uh, changes from the MySQL database captured into DMS, streamed to Kinesis, being consumed via the Spark application, and put into Delta tables. And these Delta tables are getting served to dashboard via the Databricks serverless SQL. So now that I have given you a fair idea on the problem statement and requirements from the new system, I would hand over to Rati to talk specifics about a few of the implementation details and challenges we faced and the results. Yeah, over to you, Rati.
Thank you so much, Rohan. So now that you guys have broad level understanding of the solution, let's deep dive into it. Hopefully, cool. So we have used CDC ETLT pattern. CDC stands for change data capture, as has been mentioned by Rohan multiple times now. And then ETLT pattern is extract, transform, minus transform, load, and then transform again. Here, kinesis becomes our staging area of sort. A Spark job written in Scala reads the data from kinesis, it transforms, denormalizes, and then dumps the data into the Delta Lake. The entire pipeline, starting from the MySQL database to the Delta Lake, can be broadly broken into two phases. Let's take a look at them one by one, starting with phase one. The first phase forms the bronze layer, which is from MySQL to Kinesis. The pipeline is built on AWS's DMS, Data Migration Service. We had to tweak the parameters to fine tune the migration, but rest all, as you would know, is managed by AWS to a large extent. So the data in form of CDC events traveling from MySQL database reaches Kinesis by end of this phase. Let's take a look at a sample CDC event now to understand what kind of information we are receiving from the transactions happening at the MySQL DB. So this is a sample event coming from Kinesis. Looking at the sample, we can see that we have the latest image of the data, the kind of operation performed on the data, that is whether it is an insert, a delete, or an update, the schema in the table the event belongs to, and these information sort of forms the basis of our control flow for the second phase of the pipeline. So that brings us to the end of the first phase of the pipeline. Now jumping into the second phase, that is where we put all our expertise in. This is where all the major transformation happens. There are different components to it, which we will talk about in details in the subsequent slide. So I'll just take a pause for 2-3 seconds here so that you guys can just take an idea. These are basically different components of the Spark Scala application which we have written and which is running as a streaming job. Moving on to the control flow. So we won't be going into detail of every flow here. Hopefully, we'll be able to share these resources with you so that you can take a look at it in detail. However, at a high level, this represents the decision we take once we receive the CDC event data, the same CDC event data which you folks just saw a sample of in the previous slide. These decisions are based on the kind of operation that has been performed on the table, what table it was where the operation was performed, so on and so forth. Now, this may seem pretty straightforward because I think there are a lot of open source solutions available today where you can apply CDC changes to your OLAP system. However, this wasn't that easy. There were a lot of challenges, and major challenges came because of the data, the issue which our data source had. Let's take a look at them. So the data was coming from a legacy system, and one of the biggest constraints which we had was we won't be touching the existing system at all. A new solution had to be built adjacent to the existing system. To name a few of the challenges with the system we had, those were data integrity issues. The data source, the MySQL database, although a relational database, didn't have the data integrity constraints like referential integrity applied to it. This opened up a window for every single dimension being eventually consistent, which has its own technical challenges, as you would know. Another was data redundancy. The application on top of the OLTP DB does deletes and inserts instead of doing an update, increasing the actual number of operation multiple folds. This legacy system also does data acquisition multiple times a day from outside the organization with an overlapping window, which meant that it will be acquiring same data over and over again, resulting in a lot of redundant updates. Third one was the multiple one-to-many mapping between fact table and eventually consistent dimension table. I'll go with the assumption that we are aware about fact and dimension table. Also, to give an idea, the prerequisite of the solution was we transformed the data into snowflake schema. So resolving this eventual consistency issue actually was a big challenge. Resolving the volatility of the summary data actually became a big challenge due to the eventual consistency issues. By volatility, I meant the summary data or the report data which you are generating. Ideally, it should be incremental, as in when you're getting more and more data, you keep on adding on top of that. However, we were required to mutate that data, and not just mutate that data. In fact, as and when data comes, you go and update it. So even if you don't have all the data available, your summary should still be present there with placeholders. That was the requirement from product. So, and as I mentioned, the data was similar to Snowflake schema. So flowing the changes of a leaf dimension to the summary data required a full-fledged join and merge, which you would know would take a hit on the performance. So how did we solve these problems? Take a look at them one by one. So the first thing was batch apply. We added an algorithm which reduces the total number of transaction events into effective minimal. We just went through the redundant data issue, the redundant transactions which are happening on our data source, providing us with a lot of CRUD operations. So this particular algorithm which we applied, what it would essentially do is it will transform all these transactions into effective minimal. For example, if you have 100, let's say if 100 updates on the same record, is equivalent to processing just the last update event. They both will take you to the same state, essentially. Similarly, all the permutations of create, update, and delete happening on the same record can be reduced to an effective minimal. This batch apply algorithm achieves that. To expand a little bit more than that, we can talk about. So we have essentially three write operations: create, update, and delete. That would turn out to be a total of 12 permutations of these three operations, out of which seven are valid. When I say seven are valid, rest all are not valid because, for example, you can't really do an update after doing a delete, right? So out of all these 12 permutations, only seven are valid. Out of the seven permutations, four needs two operations, last two operation, and three needs just the last operation. So even if on the same record you're doing create, update, delete multiple times, you essentially need to just process the last two or last one event. This effectively reduced the number of transactional events we were processing, reducing the overall performance and cost impact to a large extent. The other big challenge which we had was the eventual consistency. As described earlier, the majority of the dimension tables were eventually consistent, which meant we couldn't have gone with a non-volatile denormalized data. That is, we couldn't have waited for all these values to come and then we prepared the summarized data. So for a non-volatile data, we would have to wait for the dimension to prevent before we perform the join, right? However, our requirement was that, as I mentioned before, also from the product, that the data should reflect as and when it's available on the source. This essentially meant that we merge the dimension in the denormalized data as it comes. The solution was bound to take a hit on the performance, as you would know, merge operations are quite expensive. Fortunately, we had time as one of the sub-dimensions of these eventually consistent tables, and time was also one of our partitioning columns. So what we did was prepare denormalized data for the recently received dimension using broadcast joins, and then merge the data with the existing denormalized data with low shuffle merge enabled. Low shuffle merge is a property which you can enable with Delta file formats. The entire processing was within our SLA. However, it still remains under the scope of future improvement for us. This wraps up with the processing side of things which we wanted to talk about. Let's talk a bit about warehousing now. So just let me take a check on the timeline. We're good. Data warehousing. So we have chosen Delta storage framework for our data lake. Delta was part of our existing ecosystem, and we are also using Databricks runtime for Spark processing job. The inline processing application, which we talked about just now in detail, that is also using Databricks runtime environment. So as you would know, Delta gels pretty well with the Databricks runtime environment and with Spark. However, that was not the only reason. The performance which we required and few of the requirements we had, like schema evolution and enforcement and rollbacks, those are all available with Delta. So although we had other options with us, but we didn't find it substantially better to move out of the existing ecosystem. So this completes our entire solution. Let's talk a bit about optimization, some of the techniques which we have used. So these are some of the common optimization techniques which we have used, like low shuffle merges and z-order indexing. Nothing state of art here, but we had to apply post-processing. The one thing which we would want to emphasize on is, although when we built the solution, the performance was quite well, but as you would expect, over a period of time, because this is incremental data, your performance is going to degrade. So you will have to have some sort of a strategy on your post-processing optimization, which you can run at a regular interval. So the z-order and the pruning part actually falls under that. So we regularly do this. We regularly ensure that the indexing happens on a regular basis on the data, so that not just queries storage is optimized, but also the querying on this data is optimized. As you would have noticed that the entire solution moves data across multiple hops, which means that there are multiple point of failures as well, right? Data is starting from MySQL to DMS to Kinesis to the inline processing job, and finally getting dumped into the Delta Lake. There's a possibility of things going wrong at any point in time. So how do we tackle that? So to tackle that, what solution we have is the checkpointing. We have checkpointing in multiple places. To name a few, DMS has its own checkpoint available, and then the inline processing job, which we have written, also has checkpointings. um, so if something goes wrong at any point in time, all we need to do is do a retry, and the processing will be picked up from the last checkpointed stage. Uh, we did end up adding duplicate handlers for the retry batch at a small performance cost, because our checkpointing happens at every single batch. So let's say a batch, we have started processing a particular batch and something goes wrong in between. Then when you do a retry for that particular batch, there will be duplicates. So the reason why it will have a performance impact if you have duplicate handlers is, if you might be doing appends for certain use cases, you will still have to go ahead and do a merge or an upsert because you may have duplicates over there. So apart from this, no significant issue as far as achieving resilience is concerned. And again, because this is going to happen just for one batch, the batch which you have retried, so it wasn't a concern for us to have this implemented. Finally, our performance comparison with the old solution. The red bars represents the old solution numbers, and the blue ones the new one. So with the old solution, what we were able to achieve for a concurrency of 16 users, average data volume of 140,000 records in 70 seconds, we are able to achieve the same within 7 seconds, with a tolerance in increase of concurrency up to 70 users, data volume up to 2.4 million records. So this result was as required with the change in condition for the next 2 years, as was projected by our product team. And this is sort of expected as well, because we had moved from a ROLAP solution to a non-traditional MOLAP solution. You can still call it MOLAP, although we were not building any specific cubes. We are dumping data in a format on top of which you can generate as many cubes as you want in a fairly small amount of time. So this is something which was expected also as well. So that's all that we had to share with you people.